Hello, my name is Alan Rose from Corrdesa, and today I'm going to show you how our technology can shut down galvanic corrosion while eliminating cadmium. As a company, our mission is to help our clients quickly develop, qualify, design, and implement corrosion-resistant materials and coatings that meet regulatory requirements such as REACH, EPA, OSHA, etc. And we do this by leveraging our engineering simulation expertise, which helps us to significantly reduce the time taken to qualify these materials, and at the same time gives us a great insight into how these materials work. Our vision is to become a key company in this area and the company to consult for corrosion solutions. So, a little bit of background on Corrdesa. Well, we are already experienced in transitioning and deploying a new technology. As an outcome of another Navy SBIR, we actually developed and commercialized Corrosion Gin, an award-winning galvanic corrosion software tool for assessing galvanic corrosion risk. This has been released as a SaaS tool, that is software as a service. This is itself a growing business model, highly scalable and monetized through licensing. From a marketing perspective, we have teamed up with initially two organizations, a large multinational engineering company and also a global publishing house. And each of these licensing agreements extend our global reach, providing opportunity for significant growth. We have unique R&D expertise, particularly in the laboratory, where we have developed material screening protocols. Indeed, one of our protocols was adopted by NAVAIR, the Navy Air Fleet, in order to standardize a process for consistent and robust measurement of polarization curves used to support the data acquisition needed for an upcoming revised military standard, MIL Standard 889D, for dissimilar materials. We have developed many coatings and processes which have helped us to also hone our skills in framing, testing, and qualification programs. As I said, engineering simulation is very much a technology that we embrace. It gives us great insight and it allows us to assess and test innovative ideas such as our new scalable electrode design, for which we have a patent pending. I personally have always been an advocate of engineering simulation capability. For aerodynamics, simulation technologies provide essentially a digital wind tunnel, and for our sector of materials development, we think of simulation as providing us with a digital corrosion test chamber that runs in a fraction of the time compared to, say, a 40-day physical test. Our staff comprise a number of experts in their field. Our CTO, Dr. Keith Legg, for example, has more than 35 years experience of qualifying new coatings, during which he has played a significant role in hazardous coatings replacement technologies, such as replacing chrome. He is presently working with the DoD, Department of Defense, on the reduction of chromates. Not only have we transitioned and commercialized a software product, we've also developed and manufactured and sold mobile non-drip plating equipment, such as the zinc nickel plating equipment, which we sold to the F-35 program. They purchased 50 of them recently with options for more. The Navy Challenge. With the carbon fiber composite panel removed, the photograph on the right shows a widespread corrosion around fastener holes on the airframe structure of an FA-18. From a number of such teardown inspections, the Office of Naval Research has learned that 75 to 90% of structural damage is actually initiated at galvanic interfaces. To repair these holes, the corrosion is removed, which often enlarges the hole, which needs to be brought back into dimensional tolerance with bushings. This is a very labor-intensive process. Plus, these bushing airframe interfaces will themselves cause galvanic corrosion. Presently, the strategy for treating such bushing interfaces is to use a protective or sacrificial coating of electroplated cadmium. This actually requires a substantial process infrastructure, which results in long turn times and the risk of exposing personnel to toxic materials. Additionally, there is a global move to eliminate cadmium, so over time, there are less and less facilities that can actually plate the cadmium. As a consequence of all this, the Navy require a faster, safer way of treatment to minimize galvanic corrosion risk, without the use of cadmium, particularly at bushing interfaces. Our solution is reactive pigmented coatings, or RPC. If you take a look at the photographs on the right, you can see a bushing inserted into an aluminum structure. Despite the use of corrosion-resistant steels in the top image, area A, you see the impact of the galvanic corrosion between the untreated steel bushing and the surrounding aluminum structure. Whereas in area B below, when the bushing is treated with cadmium and wet installed with a standard hexavalent chromate primer, galvanic corrosion is avoided. However, we want to eliminate the use of the chromate primer, so we replace that with our reactive pigmented coating. Indeed, Corrdesa also has technologies to replace a cadmium plating with zinc nickel, so the whole bushing process can be replaced with much safer materials, which delivers some significant benefits. The RPC is easily and quickly applied, simply brushed or sprayed on like paint, and it is non-toxic and consequently much safer. In a previous Navy SBIR, Corrdesa developed a complex simulation technology that enables us to computationally optimize and then formulate reactive pigmented coatings for different repairs and scenarios. We are leveraging the simulation technology to specifically design a reactive pigment coating system for the use with such bushings. This present technology is at TRL4, and we expect to get it to TRL8 in 2022. What is our current status? Well, an RPC system that has already been extensively tested is the aluminum-rich primer from Navarre. In the photograph below, you can clearly see how the RPC primer performs much better than the typical primer system, the scribe panel on the left showing much less corrosion. Corrdesa's proprietary computational algorithms and workflow have provided us with incredible insight into how these sacrificial reactive pigment coatings actually function. In the computer model, we can choose particle size distribution, loading, and resin properties, and then predict the effective protection. In this way, we can optimize the necessary process parameters upfront of any formulation, drastically reducing the timeline for development and testing. So, where are we going with this technology? Well, here is our plan. We have developed and refined our computational workflow for these bushing scenarios, and using AI-based optimization techniques, we have down-selected our top-performing reactive pigmented coatings. These formulations have now been manufactured and are being applied to panels for accelerated corrosion chamber tests, which are presently ongoing. There has been a delay in this since these coatings are actually taking a very long time to corrode, which is of course a good thing. Anyway, the next step will be beach exposure tests, which have much more fidelity than the chamber tests, and then aircraft denval early next year. To summarize, the use of our computational simulation techniques has significantly contributed to the development of these coatings and their enhanced performance. We see opportunities for custom development of further reactive pigmented coatings for other specific applications, both in aerospace and other sectors such as infrastructure, like painting and protection of bridges, for example. So we are very interested in opportunities to talk with folks here that would like to explore the benefits of the RPC coatings for their products and needs in particular. Why should you use a wet install RPC system? Well, here's some reasons. The coating is easily applied, brushed on, or sprayed on just like paint. There is no need for any expensive or complex equipment or special plating facilities. This significantly reduces the turn time by a large fraction, more than 80%. And you can perform the repair in forward locations also. The aluminum reactive pigment coating protects a component even when the coating is actually breached. So when areas of the coating is damaged, the protection is ongoing, resulting in longer times between maintenance cycles. Also, the reactive pigmented coatings are non-toxic, providing a safe replacement for cadmium, reducing exposure risk to our operators and ensuring their ongoing health and safety. So, let's take a quick look at some other opportunities. The elimination of hazardous materials is a top priority for many organizations, such as the Department of Defense and their supply chain. It is, of course, important that the replacement materials must function at least as well as these legacy coatings. Consequently, the development process takes a lot of time, but using our computational techniques, we can make significant impact on this. Also, reducing galvanic corrosion risk is a common need across all types of aircraft, new and legacy. We can see opportunities with the helicopter fleets with the US Army and the US Air Force, as well as other military platforms and civil aircraft. There are also opportunities for RPC coatings in other sectors, such as infrastructure, bridges, and construction. Our strategy is to partner with commercial producers and license our optimized RPC formulations. To finish off, please contact me if you want to know more about how we can eliminate cadmium for the protection against galvanic corrosion on your products and systems while simultaneously reducing turn time and keeping your workers safe. My contact details are shown here on this slide.